Okay, question 11. Question 11 is just your simple question on lever. So obviously your purpose of the spanner is so that you can use less force, and that is because you have a longer D, and therefore small force can produce the same moment required to tighten the nut on the bolt. So that's why your answer is A. Question 12. Question 12 is about your energy conservation. So you need to first determine the initial point and the final point. So I take the initial point as when the bullet is just traveling in air. So all the energy the system process is just the kinetic energy from the bullet. So just take the initial velocity 300 meters per second and you find out that, okay, so in total I have 900 joules. So this 900 joules is going to be the total energy for the system at any point of time. Okay, then after that I look at the energy when the bullet has passed through the wooden block. So you see that we assume that the bullet are of the same height, so there will be no change in potential energy. So the only change here is your kinetic energy, and just put in the 200 meters per second, use the formula, you find out that, oh, now my energy in the system only left with 400 joules. So between 900 joules and 400 joules, there's a difference of 500 joules. So this 500 joules of energy which got missing must be the energy that is used to overcome the friction in the wooden block. So then I can write down the equation. The difference in energy must be equals to the work done against friction. So that's why on the left hand side I have this 900 minus 400, and down here to find the work done is just force times distance. And from the question you already know that the distance traveled is 0.025. So this is your unknown, then work it out, you will get F equals to 20k. Okay? Okay, question 13. Question 13, okay. If you are to find the power output, you will need to calculate the energy, you will need to calculate the time. So definitely A is required. Let me see. So you want to ignore the work done against friction, and this work done against friction when you're running up the stair must be a horizontal force, right? So if they tell you that they want to ignore a horizontal force, meaning that when you want to calculate your work done, if you do not have your horizontal force, then you won't need your horizontal distance, right? Because that you do not know the F, what for you want to know the D, correct or not? So that's why your option B, the horizontal distance, is not required because you are anyway ignoring the horizontal frictional force. So that's why B is not required. Okay, if you look at C, because you have already eliminated all the horizontal forces, you will definitely need to use the vertical forces. So your vertical forces is your weight. So how to find the work done will be your weight multiplied by the vertical distance traveled. So that's why you need to know the vertical height of the stairs. Okay, and for your part D, the weight of the student is your vertical force. So definitely you require that. Okay. Okay, question 14. Question 14. Is quite easy. If you take the pressure of the water level at this point, okay, you can see that here at the right hand side you have the atmospherical pressure P atmosphere plus the downward P from the girl. Okay, the total pressure at this point will be atmospherical pressure plus pressure from the girl. And if you look at the pressure here, it will be again the atmospherical pressure plus the pressure from this column of liquid. Okay, at these 2 points the pressure is the same. So basically, you can see that the pressure from the atmosphere will be always there. So you can eliminate that. You will equalize. So then you can write out your equation. The pressure from the column must be equal to the pressure from the weight of the girl. So weight of the girl, you just take W over A. Pressure from the column of liquid, just use rho GH. So H is the one that you want to find. So do your algebra, you will find the answer. Okay, we'll continue with question 15. So question 15 here says that the temperature is rising, container is sealed, meaning that your volume is constant. So with these 2 parameters, you can actually deduce that the pressure must increase. Okay, so if we look at A, the force due to collision, so you know that pressure is increased and pressure is equals to force over area, and the container is sealed, so meaning that your A is constant. So when you have that, when you have P equals to FA and P has increased, A is constant, so definitely your F must increase as well. So A will be increasing. Okay, I'm going to skip B. Later I'm going to come back on this. Okay, let's look at C first. So average speed. So the temperature and average speed is related. So the higher the temperature, the more the kinetic energy. Okay, and the more the kinetic energy, the higher the speed. So definitely when temperature increase, average speed of the particle will increase. Okay, then next we look at D. Okay, because now the container is sealed, right, and the gas particles are moving faster, so definitely the frequency of collision will increase. Okay, now I want to go back to B. Now average distance here is quite tricky. You have to imagine that you are able to take snapshot of the system, and then from this snapshot you are going to measure the distance between the gas particles, and once you have that value, you take the average, okay, of the distance that you measure from the different snapshots. So how can we imagine, how can we interpret this is that, okay, if we have already established that the frequency of collision is going to increase. So if now you start taking snapshot, okay, of this whole system, okay, the chances of you finding the particles are colliding with each other must be higher, right? Because now the frequency of this occurring is higher. Okay, so the chances of you getting a snapshot of the particles are colliding with each other is higher. So if the particle is colliding with each other, the distance between the colliding gas particle must be 0, right? Meaning that if you take snapshot, the chances of you finding the average distance equals to 0 will be higher, right? And therefore, because of that, the average distance that you are going to calculate with the different snapshot will definitely be higher. So therefore, your average speed must decrease. Okay, I'm going to draw it out, okay? I know that just by saying it's very hard to imagine. So this is on question 15. So let's say you have before hitting and you have after hitting. Okay, and before hitting you are going to take snapshots. Okay, you take, let's say, 5 snapshots. Okay, among these 5 snapshots, okay, you find that, oh, okay, you have captured like one of it, the 2 gas molecules are in collision. So because in collision, the distance here will be 0. Other than that, you have, I don't know, snapshots whereby the distance are all different. So here you may have distance equals to 10, distance equals to 2, distance equals to, I don't know, 5, distance equals to 8. Okay, just like that. Then after that, you go and take the average distance. Okay, so after hitting, again you take 5 snapshots. Okay, and previously in part D, we have already concluded that the frequency of collision must be higher. So out of these 5 snapshots, you find that, oh, okay, I found this one is colliding. Oh, this snapshot is also having collision. This snapshot also having collision. So among the 5 snapshot, you have 3 that has captured collision, because now the frequency of collision is way higher, right? So this one will D equals 0, D equals 0, D equals 0. Okay, and all the other snapshot, okay, they could be far apart, okay, it's alright. Okay, they may be close apart, it's okay. But the thing is, because after hitting, you are going to get more snapshot showing you a collision. So because of that, when you take the average for this after hitting scenario, will definitely be much lower, right? Because you have more 0 values. So definitely your average is going to decrease. So therefore, in your option B, the average distance of the gas particle must decrease. Okay, that's the reason. Okay, now we move on to question 16. So question 16 is about Brownian motion. Okay, what you can see, you cannot see the gas particle. They are too small for the microscope. Okay, the microscope cannot see molecules. They can only see dust particles. So what you are seeing is actually the dust particle. So option C and D will be still in. So they are not actually vibrating in their fixed position. Okay, they are actually being knocked randomly on every direction by the moving air molecules. So definitely it is not by their fixed position, they are moving in a random manner, because your air molecule hitting them is also moving in a random manner. Okay. Okay, question 17. 17 is about your cooling fin. I think number 2 and number 3 is quite obvious. Number one, it is quite uncommon to see that they are talking about conductor. I'm still not very comfortable with the fact that they say that okay, it is a good conductor, and so it's going to conduct it quickly to the environment. Now the thing is that the heat transfer method between the fin and the environment mainly depends on convection. Okay, meaning that the air around the cooling fin actually absorbs the heat, and because of that, density changes, and then they start carrying the heat away. But we cannot deny that the cooling fin are made of good conductor, and good conductor actually facilitate that transfer of heat energy between the fin and that layer of air around the fin. So I will still agree with 1, but personally I think that they are using good conductor to draw the heat out from the object that you want to cool to the fin. Okay, that is I think the main mechanism. Okay, between that the object may be a microchip, okay, to the fin, and the fin has to be a good conductor. If not, you cannot draw the heat out from the microchip to the fin. Okay, so anyway, although it is not the main heat transfer method, good conductor does have that, so let's agree on that. Okay, for your question 18, you can use the formula. For me, I always think of this as a linear graph. So you know that your temperature is here and the change in length is always here, so you have a straight line. So just find the gradient here, find the formula of this line, and you can get the answer. Okay? Okay, question 19, your kinetic model of matter. Best describe water at 0 degree and it is freezing to ice. So the context of the question actually indicate that there is a change of state. So when there's a change of state, you need to know that the internal kinetic energy will be constant, and the internal potential energy here, because it's freezing to ice, the potential energy would decrease. Decrease. Okay, so the intermolecular form, when you are changing into solid, must be forming. Okay, so B and D definitely out because it says that it is broken. So then you look at what is written behind. So if you look at A, the water molecules greatly slow down. Okay, now the thing is that if it is undergo state change, kinetic energy is constant. So therefore, the movement, your speed, your average speed of the water molecules must remain constant as well, because the speed actually depends on the Ke. So if here is written greatly slow down, it is actually indicating that the kinetic energy is decreasing as well, and this does not happen when it is going through a state change. So that's why your A is also out. Okay, so if you look at C, it says that the average speed of the water molecule actually remain the same. So this actually implies that the average Ke is also remaining constant, which fits into the kinetic model of matter. Okay, when the matter is changing state, the Ke will remain constant. Okay.